Hello, and welcome to this video on welding symbols for groove welds. To begin with, let me start by sharing the screen so you can follow along with the PowerPoint that I'm going to use. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting business is on the web at welding-consultant.com, and you're going to find this video on my YouTube channel at Weld Nugget. In this video, we're going to look at welding symbols for groove welds, an introduction video where we're going to review the different types of groove weld designs and the reason why we would choose one over the other. We are also going to introduce the concepts for back weld and backing weld. If you're new to the welding business, it might be better to review the other videos that I have already posted on my YouTube channel, especially an introduction to welding symbols. That will be a very useful video to watch, and types of joints and welds. And those two will clarify some of the concepts that we might be introducing over here. In addition to that, there are other videos on TIG, MIG, and laser welding, which you might also find useful to appreciate the contents of this video. What is the definition of a groove weld? A groove weld, and as defined by American Welding Society, AWS, 3.0, that is the document number. The name of the document is Standard Welding Terms and Definitions. The American Welding Society defines the groove weld as a weld in a weld groove on a workpiece surface. That is one of the options. And I have listed those four options, 1, 2, 3, 4 over here, and shown those options schematically as 1, 2, 3, and 4 over here in the picture. A weld in a weld groove on a workpiece surface, that is the first option. That means, let's say you're welding two plates and the plates have a surface, and the end of the plate where the plate is cut is the edge. And you have made some grooves on the surface, and then you're welding in the groove itself. What you're seeing over here is a schematic of what the solid lines show what the weld was like before welding. The components were before welding, and after welding, that area, that volume which is shown by this darker gray zone, that is the weld zone after welding. So that would be all filled with molten metal, which then would solidify. And then if you take the weld and cross-section it, you're going to see that weld zone in cross-section. So these are schematics of these cross-sections. They are not real images, obviously, but this is just to clarify what the text is saying. So first option is a weld in a weld groove on a workpiece surface. So a configuration like this would qualify. The second option is between workpiece edges. So if you take two edges and butt them together and make a weld, and as we see over here, that weld would qualify as a groove weld. And then between workpiece surfaces, so you can actually take two parts and put them on top of each other, but as long as you can bring the energy from at an angle and make a weld which the weld zone looks like this, then that would also qualify as a groove weld. And lastly, between workpiece edges and surfaces. So this is a configuration where you can see we are making a weld on a surface of one of the components and on the edge of one of the components. And if you're familiar with welding, you will identify this as a T-joint with a groove weld. So those four are the options. All those would be considered a groove weld as far as American Welding Society is concerned. Let's dig in more into the weld groove definition. What it doesn't say is also important. It does not specify the process. So any process that can form a weld along the interface could be considered a groove weld. Conventional processes for making groove welds are typically arc welding, laser welding, and electron beam welding. But there are other processes such as flash welding, upset welding, friction stir welding, and thermit welding, which also can make welds which look like number 2 over here. So those will also be considered to be making groove welds. The definition does not specify if a filler metal is required. So you don't have to use a filler metal. You can make an autogenous weld. Autogenous weld is one where we don't add a filler, but just weld the parts themselves to each other. And thirdly, it does not specify any direction of any energy delivery. So you can make the weld from the top, from the bottom, and there are some processes where the direction doesn't matter because the welding happens at the entire interface at the same time, such as all of these processes I mentioned before, like flash welding, upset welding, and so on. So all of those can classify as groove welds depending on the conditions. Let's look at the simplest of the groove weld design, square groove welds. The square groove welds are defined as welds between two parts where the edges are getting welded together. So if you look at this diagram over here, the number 2 would qualify as a square groove weld. Here we are showing the weld symbol, the welding symbol, and the weld symbol for square groove are these two parallel lines. These two parallel lines are below the horizontal line. So we are making the weld on the arrow side. That means the energy is going from the top. Whenever energy goes from one side, the weld tends to be wider on that side, usually on that side. And that's how we know, that's how the cross section would look like. So if you take two parts and weld them together with say TIG, MIG or something, you and your cross section, the weld zone would be wider on the top and narrower towards the bottom. In the tail of the weld, we are seeing CJP, that means complete joint penetration. That means in this case, the design engineer expects us to make a weld which penetrates throughout the thickness of the weld and actually protrudes a little bit on the bottom as well. Now here we are defining this for a thickness of T. And what we are looking at over here in the table below is single side penetration limits for each process. So we are saying we want to make a square groove weld that is good. We want to make it from one direction, one side, so from the arrow side, so the energy is going to come down over here. But what is the thickness of these components that we can weld with different processes? And these numbers are for reference only because every material, every component, every equipment will have pros and cons and advantages and disadvantages. And they might be able to make thicknesses which are greater or lesser than these numbers I've listed over here. But this is just to give you a ballpark number. So arc welding processes, which are commonly used, such as TIG, MIG, and stick welding, they can go up to a 16th or an 8th of an inch. So about 1.5 to 3 millimeters, depending on the metallurgy. Plasma can go slightly deeper than that. Processes such as submerged arc welding and friction stir welding can go up to 3/8 of an inch, about 10 millimeters. And laser welding, depending on the quality of the laser and power of the laser, can go very deep. So I've listed 1 inch over here, which is not very common. But if you have high enough power lasers, you can go 1 inch and even greater now. But typically, you would go an eighth of an inch or a quarter of an inch with, say, 1 to 2 or 3 kilowatt laser. Electron beam welding also can make very deep welds up to 2 inches plus, and that is the whole range of welds. So we can go all the way from a 16th inch deep weld, possible with, say, stick welding or MIG, all the way down to electron beam weld, which would be 2 inches or more deep. Now, the reason why this is important to know, because as a manufacturing engineer, if you come across a drawing which says that we want to make a full penetration weld with TIG welding and it has to go 3/4 inch deep, then it's not going to work. So you have to then approach the design engineer to review the situation and figure out what are the options where you can go CJP on a material which is 3/4 of an inch with a certain process. There are situations where we don't have to go full penetration, and that is, weld is called PJP, that is partial joint penetration. So the design engineer may require only a partial penetration. So we can weld something which is thicker than T as long as we don't need 100% penetration. Another option is we can weld from both sides. Then we can weld from one side and then from the other side. And now we can weld thicknesses which are twice as thick. In this case, the welding symbol will show the square groove symbol below the line and the square groove symbol above the line as well. And it says CJP and it will specify a particular process. So we can go thicker if you have access from both sides, though that is not always the case. Many a times we don't have access from both sides and we may have to go for some other options. I had mentioned earlier that some processes are not directional in the sense that the energy is not coming from vertical or from above or below. The energy is created across the entire interface. And here again, the welding symbol will show that we have square groove welds from both sides, even though we are actually not providing the energy from both sides. The energy is produced all over the surface without any direction. And here, we'll have to specify the welding process, such as in this case, flash welding. So I'm showing you a cross section of a flash welded piece. So these two pieces were flash welded together. And during the flashing process, you will see material squeeze out on both sides. And you could actually clean up this thing and machine it off and make a very smooth surface on the top. So there are processes such as flash, upset, friction, and thermit welding, which will use this symbol, but they don't have truly a direction, and you have to specify what process you're going to use. If you're welding, say, a square groove weld with conventional techniques such as, say, MIG welding or TIG welding, and you come across a thickness which is much greater than what the process can handle with a square groove, then the option would be to go to a V groove design. A V groove design, this is similar to the configuration I had shown in number one. In a V groove design, we make a groove on the weld surfaces, and this allows the welding torch to go down and make a weld which will fuse the bottom of the parts also. Here we are assuming that we are not going from both sides, we are just primarily going from one side, and we make a weld. So this is the part what it looks like in cross section before welding. This is what it would look like in cross section after welding. And here we can see the weld symbol. The welding symbol is the whole thing. The weld symbol is the specific V shape, and that defines the V groove design. Now this V is below the horizontal line, and that shows that we are going from the arrow side. So energy is coming from the top. And this is CJP, so we want full penetration. So the way this is done is usually the way this is done is you make the root pass as the first pass. So root pass happens first. That fuses the root over here. This is the root of the weld. The bottom of that V is called the root. And then you add fill passes to fill up that V shape and to have certain profile on the top. And that can depend on thickness of the part. That can be two fill passes, 10, 15, 20. I have done parts which are up to 20 fill passes. So that is pretty interesting. The V in the V groove is shown with a 90-degree angle always. So the angle between the two lines is 90 degrees. Even though the V itself in the actual component, this angle may not be 90 degrees. This might be 45, 60, 120, it could be anything. But the V itself as drawn is shown as having 90 degrees. Now this is a V groove design. Later on, we're going to talk about U and J groove also as the parts become thicker. So now let's see what happens with the root pass. The root pass is the most challenging of the welds in a groove weld. I'm showing you here in a schematic form. The two parts are being welded. The torch has come down. There's an arc, and there's a lot of molten metal over here. At the conclusion of the weld, this molten metal will freeze and make a weld. But at the moment, as the argon gas is being sprayed from the top, it is possible that the bottom of the weld from the root side is exposed to air and moisture in the air and can get contaminated. So one of the risks of root pass is the root pass can get contaminated by the environment. Now there are options to that. If you have access to the root side, we can put some fixtures on the bottom and expose the root pass on the other side also to argon, and that kind of takes care of the issue. That is quite commonly done in welding of stainless steels. The second issue is control of the molten metal. It is very difficult to control this molten metal. So we want to make sure that the melting is enough that you have full fusion. So the entire root, and you actually see some of the molten metal come down on below into the root, beyond the root. a little bit. At the same time, we don't want the molten metal to drop down because that's going to be impossible to fill back. So controlling the molten metal is also very challenging in the root pass. So there can be situations where the filler alloy that you use for welding, the fill passes could be different than the filler alloy that you're going to use for the root pass. So you could have a different alloy for both. Again, this has to be certified and qualified before, and it has to be in the WPS. So we have the authorization to use a different alloy in the root. Argon is one way to shield the other side, but sometimes other options are used, such as a backing plate or a backing weld. Here I'm showing you a welding symbol of a backing plate. Here again, it's a welding symbol, and the V groove symbol is below the line, and there's a rectangle above the line, and so that rectangle is coming from the other side. So other side is the root side. So arrow side from the top, root side from the bottom over here. So backing plate can be placed over here. And in some situations, the backing plate is almost the same as the base metals, and the backing plate actually gets welded into the weld and remains there. So it's not removed. But there are situations where you don't want the backing plate to remain in there, especially such as inside a pipe where the flow of the water could be obstructed. So there you may have a backing plate which is removable. And if it is a removable plate, then the letter R shows up in that symbol. Using a backing plate is one option. The second option is to use a backing weld. So a backing weld is a small weld which is made from the root side before the root pass is made. And then you make the root pass and the fill pass and so on. And in this case, the backing weld symbol is a small half dome above the horizontal line. So the backing weld is being done from the root side, and then the V groove is made from the arrow side. So these are the two choices, backing plate or a backing weld. A third choice is to make a back weld. A back weld is made after the entire weld is complete. So the back weld goes in a different sequence. So first of all, step one, you complete the V-groove weld. So that means you make the root pass and the two cover passes, two or more, whatever is required. And then you go back from the root side, and assuming if there is contamination in the root pass, if there is any contamination in the root pass, you can actually remove portions of the root pass by gouging. You can gouge it out and then fill it back up with back welds. Again, the back welds can be a single weld or a double weld or three. And again, you don't have to gouge it out. There are situations where gouging is not required. The welds are fairly clean. All you have to do is put down one or two backing welds to reinforce the root, to reinforce the strength from the other side. Here again, we see the welding symbol. We have the V groove symbol below the line. And above the line, we have this open, the dome, which is not filled, and that is a back weld. Now you will see from the previous slide I had presented that the backing weld symbol is the same as the back weld symbol. Now that might sound confusing, but there is a reason for that. The reason is that a back or a backing weld is an option for the manufacturing team. So the design engineer might leave it to you, the manufacturing engineer, to decide whether to go with a back weld or a backing weld. And there are situations where the design engineer might choose not to do that. They might specify which weld they want to be made, either as a back weld or a backing weld. And in that case, they will specifically say that in the tail of the weld. In the tail of the weld, it'll say back weld. Another way to show whether they want a back weld or a backing weld is to show the sequence of events, sequence of welding. So in a back weld, the sequence is such that you first make the V groove weld and then go back and make the back weld. And there might be some more details about gouging or no gouging and so on in some documentation. But here we can see the sequence. We are making the V-groove weld and then making the back weld. So in this sequence, the first weld, which is closest to the tip of this arrow, is made first. So in this case, V-groove is made first, and then the back weld is made afterwards. If the design engineer wants us to go the other way, they can specify it in the tail, or they can split that sequence and show it explicitly, where now the first weld made is the backing weld, because we are now making the weld before the root pass and everything is done. And then you will come back from the arrow side and make the root pass and fill passes. So there are two ways to indicate the sequence of events. Either you write it in the tail saying it's a back or a backing weld, or you can split the sequence. Now, this splitting the sequence is actually quite common. You can have other operations in there which are related to welding, perhaps starting with some cleaning, some welding, back weld, backing weld, and V-groove, and then some perhaps machining of or post-process of the weld itself, and then maybe even a non-destructive technique. So you could have multiple lines in here. Right now I'm showing 2 lines on each side. In V-groove designs, there are multiple choices depending on size, thickness, access, and compatibility to the process. Here I'm showing you the V-groove design that we have been talking about. But if the parts are thicker, or let's say if the parts are very thick and you don't want to make a giant V groove, you can make a double V. Of course, you have to have access from both sides. So if the parts are much thicker, instead of V groove, you can make a double V. But now we have to weld from both sides. So we have the V groove symbol above the line and below the line as well. So we're going to make the weld first from one side, flip it over, and make the V groove weld from the other side. In some situations, it is not easy or possible to make a V or a chamfer on one of the components. For example, in this configuration I'm showing over here, this is a T-junction. So there's a flat plate and there's another plate coming over here in a T-junction and making a weld. So in this case, it is fairly reasonable to make a groove on this component, horizontal component over here, but the vertical component, which is a plate, would not be feasible to make a groove in that one. So now we have to make what is called a bevel groove design. That means there is the groove machining is done only on one component, not on both. And here the symbol is shown differently. There's a vertical line and then there's an angle line at 45 degrees. You can do that on both sides of that component. So you can have double bevel groove. So you can have groove on one side, on the other side. And it doesn't have to be on the same side necessarily. You could potentially have a bevel on one side on one component and a bevel on the other side on the other component. So there is nothing to limit that as long as these things can be made. Now, as the parts become thicker, it becomes even more difficult. Even for the V groove becomes challenging, because as the parts become thicker and you want to have a reasonable chance to make a good root pass. So this portion over here, this face over here cannot be very thick. So if you make a very big wide V groove and a small face over here required to make a root pass, then the size of the V would be gigantic and you'll have to fill the whole space. And that's why once we get to a point where the thickness of the components is more than 3/4 of an inch or 18 millimeters, we go to a U groove design. So instead of a V profile, we are making a profile which looks like a U. And the symbol over here is as shown. There's a small vertical line and there is a semicircle over here. It looks like an upside down wine glass. So what are the pros of the design? The pros are that we can make the root over here is fairly thin and it is easy to comfortably make a root pass with full fusion. Another benefit is because this wall goes up much faster and vertically, then we can actually fill this space up with much less number of passes than if we had like a giant V shape. Secondly, we have less distortion because less welding, less heat treatment, heat inputs, less distortion. And finally, the cons is it is much more expensive to make that U profile. The V profile can be made quite easily in many different ways. Water jet cutting, laser cutting, on a bandsaw, somehow you can make that V cut, even plasma cutting. But the U profile has to be machined. So obviously, it's a much more expensive process. So you would use U groove designs only if you had to, and the V groove design is not working. Just like the V groove, we have multiple choices for the U and J groove design. So if both components have the feature, the radius feature like that, then it's combined together, it looks like a U. And if you have more thickness and you want groove welding from both sides, either because it's very thick or you want some balancing of the the contraction and expansion, then you can have a double U groove design. Here again, if you want to go with a T-junction, T-joint, and only one side can be machined, then you have what is called a J-groove design. In a J-groove design, only one side has the machined feature, the other side is flat. And the symbol over here is shown as a vertical line and a quarter of a semicircle over here, a half of a semicircle over here. So it's a quarter of the circle over here. And it's always shown on the right hand side. So the quarter circle is always on the right hand side. It's not on the left hand side. It's always a vertical line and the quarter circle on the right hand side. If we have the J on both sides of one of the components, then you have the double J groove. So similar to V groove, we have similar layouts over here. Again, the only difference is the U and J are much more expensive to manufacture. There's another design called the flare groove design. A flare groove design is one where one or both of the components have a circular profile. We see over here, we are welding two pipes together, and the symbol showing over here is a flare. So these two arcs going away from each other is the symbol for a flare groove design. So if both of the surfaces have a radius feature, like in this case, we are welding two pipes, then this will be called a flare V groove. If only one of the surfaces has a profile and the other one is straight, then this would be a flare bevel groove. Flare V groove has two flare sides to it. The flare bevel has one vertical line and a flare on the other side. Again, the flare is always on the right hand side. Even though the weld can be left or right, it doesn't matter. The symbol doesn't change no matter what the orientation or configuration as this is. One of the interesting features of a flare groove design versus a V or U or J, in the V and U and J, the expectation is that at some point you're going to fuse the root. In most cases, it doesn't have to be, but in most cases, you're going to be fusing the entire root over here. The difference is in flare bevel and flare V, there is no expectation for the root to be fused. So you are likely to see a gap over here between the weld and the root point over here in both these designs. So these are the many choices you have. You have a square square groove, V groove, U, J, and flare groove design. So many choices, again, based on the design, based on the metallurgy, based on the size, based on the capability of the equipment you have to choose one versus the other. So in summary, groove welds can be made in multiple configurations, including butt joint, T-joint, and lap joint. So keep in mind, the joint and weld are two different things, and we have talked about that in the previous video on joints and welds. It is already posted on the YouTube channel. Groove welds can be made by many processes. It doesn't have to be a known process like arc welding. You can have flash butt welded groove joints or fillet thermit welding. And you don't have to use a filler. You can use autogenous welding, which is quite common in, say, laser welding and electron beam welding. Square groove welds is the simplest design, are suitable for thin components, but as components become thicker, and we have to add a filler so that we can actually go down and fuse the root and then fill it up with the filler alloy, we have to migrate to either a V groove or, for thicker components, a U or a J groove. Some of the components might have a natural profile to them, such as if you're welding two pipes or a stamped or flange component to a straight component, and that is called flare groove or flare V or flare bevel groove designs. So there are multiple choices. So just in groove designs, there are many, many choices, and you have to choose the right one for a particular application. There are some good reference documents. The AWS A2.4 is the standard symbols for welding and brazing, and AWS A3.0 is standard welding terms and definitions. AWS is the American Welding Society, and their symbols and standards and definitions are a bit different than European welding symbols. So if you are working with in different parts of the world, you will have to refer to different documents. They are not terribly different, but there are some minor differences between the two. Okay. Well, I want to thank you all for your time, and if you're in an interest and patience in watching this video. If you're interested in learning more about welding and joining, please subscribe to this YouTube channel by clicking the subscribe button at the bottom of your screen. On this YouTube channel, I have many different playlists, including that for resistance welding, laser welding, arc welding, welding metallurgy, and welding design. So I'm sure you're going to find something interesting over there. And again, I want to thank you all for your time and wishing you the very best in learning more about welding and joining. Take care.